Dr. Avijit Kar Gupta, Associate Professor, Department of Physics, Panskura Banamali College, West Bengal, India. Here, I should mention you that this webinar is designed primarily for students. If you have any question during this webinar, please write it in the message box. Our speaker will address it during the interactive session, which will be after this webinar presentation. And if you are keeping your microphone on, I will request you to keep your microphone in mute mode to avoid background noises that may distract you from listening the webinar. Now, I will request our Honorable Principal Sir, Dr. Somen Chando, Fakir Chand College, to deliver inaugural address. Please, sir.
Thank you, Broglie. I am very pleased to be present in this webinar. A very good afternoon to the distinguished guests, speaker, titled Quantum Mechanics with Python has been arranged in collaboration with the IQAC of our college. Thanks to the organizers. As a student of physics, I always enjoy lectures on the subject because it ignites some new thoughts, some rethinking, some revisualization, some new angles of view in me. I hope the audience will allow me to say a few words, a brief account of the history of the subject before the honorable speaker delivers his lecture. Quantum mechanics is a fundamental theory in physics that provides a description of the physical properties of nature at the scale of atoms and subatomic particles. It is the foundation of all quantum physics, including quantum chemistry, quantum field theory, quantum technology, and quantum information science. Quantum mechanics was developed over many decades, beginning as a set of controversial mathematical explanations of experiments that the math of classical mechanics could not explain. It began at the turn of the theory of
Sir is most probably not audible, Varnali, right now. Is it?
Yes, I thought that my connection was lost, but I think he is not audible.
He's not audible.
Yeah, he's not audible.
It's not audible. My connection was lost, but I think it's not audible.
হ্যাঁ স্যার, শোনা যাচ্ছে না। ও স্যার, আপনি মানে ঢুকতে পারছেন না আর এতে? ও স্যার, লিটনকে বলি। হ্যালো লিটন, লিটন। ও স্যার বলছেন ঢুকতে পারছেন না আর কি, বলবো? আচ্ছা স্যার, এবার ঢুকতে পার। স্যার লিটনের অ্যাকাউন্ট ঠিক আছে, আপনি এবার ঢুকুন স্যার, হয়ে যাবে। হ্যাঁ স্যার, লিটন বললো এক্ষুনি করে দিয়েছে, ঢুকতে পারবেন স্যার, দেখুন স্যার।
Hello. Okay. Okay, let me continue. So
Yes, sir.
I was discussing about the first principle, that is quantized properties. So certain properties such as position, speed, and color can sometimes only occur in specific set of amounts, much like a dial that clicks from number to number, or like the minute hand of a clock. This changed a fundamental assumption of classical mechanics, which said that such properties should exist on a smooth, continuous spectrum. To describe the idea that some properties clicked like a dial with specific settings, scientists coined the word quantized. In December 1900, Max Planck, while calculating the energy distribution in a closed hot cavity in thermal equilibrium as a function of wavelength or color, came across an undoable sum of infinite numbers. He improvised that if the terms of the infinite series are related in a definite way, namely combinations of only certain colors are emitted, which are whole number multiples of some basic value, the infinite sum can be done. And he came up with the famous Planck's radiation formula. And with the idea that somehow colors are quantized. This was unexpected because light was understood to act as a wave, meaning that values of color should be a continuous spectrum. What would be forbidding atoms from producing the colors between these whole number multiples? This seemed so strange that Planck regarded quantization as nothing more than a mathematical trick. This mathematical trick also gave us the famous Planck constant. Since the early 1800s, the science of spectroscopy showed different signature spectral lines emitted from different materials, but nobody knew why. In 1888, Johannes Rydberg derived an equation that described the spectral lines emitted by hydrogen, though nobody could explain why the equation worked. In 1913, Niels Bohr applied Planck's hypothesis of quantization to Ernest Rutherford's 1911 planetary model of the atom, which postulated that electrons orbited the nucleus the same way that planets orbit the sun. Bohr proposed that electrons were restricted to special orbits around an atom's nucleus. They could jump between special orbits, and the energy produced by the jump caused specific colors of light, observed as spectral lines. Though quantized properties were invented but a mere mathematical trick, they explained so much that they become the founding principle of quantum mechanics. Number 2, particles of light. Light can sometimes behave as a particle. This was initially met with harsh criticism, as it ran contrary to 200 years of experiments showing that light behaved as a wave, much like ripples on the surface of a calm lake. Light behaves similarly in that it bounces off walls and bends around corners, and that the crest and troughs of the wave can add up or cancel out. Added wave crests result in brighter light, while waves that cancel out produce darkness. A light source can be thought of as a ball on a stick being rhythmically dipped in the center of a lake. The color emitted corresponds to the distance between the crests, which is determined by the speed of the ball's rhythm. In 1905, Einstein published a paper titled Concerning an Heuristic Point of View Toward the Emission and Transformation of Light, in which he envisioned light traveling not as a wave, but as some manner of energy quantum. This packet of energy, Einstein suggested, could be absorbed or generated only as a whole, specifically when an atom jumps between quantized vibration rates. This would also apply, as would be shown in few years later, when an electron jumps between quantized orbits. Under this model, Einstein's energy quanta contained the energy difference of the jump. When divided by Planck's constant, that energy difference determined the color of light carried by those quanta. With this new way of envision light, Einstein offered insight into the behavior of 9 different phenomena, including the specific colors that Planck described being emitted from a light bulb filament. It also explained how certain colors of light could eject electrons off metal surfaces, a phenomenon known as the photoelectric effect. However, Einstein wasn't wholly justified in taking this leap, said Stephen Classen, an associate professor of physics at the University of Winnipeg, in a 2008 paper titled The Photoelectric Effect, Rehabilitating the Story of the Physics Classroom for the Physics Classroom. Classen states that Einstein's energy quanta aren't necessary for explaining all of those 9 phenomena. Certain mathematical treatments of light as a wave are still capable of describing both the specific colors that Planck described being emitted from a light bulb filament and the photoelectric effect. Indeed, in Einstein's controversial winning of the 1921 Nobel Prize, the work of Arthur Compton, who showed that light scattered by an electron beam changed in color. This showed that particles of light, that is photons, were indeed colliding with particles of matter, that is electrons, thus confirming Einstein's hypothesis. By now, it was clear that light could behave both as a wave and a particle, placing light's wave-particle duality into the foundation of quantum mechanics. Number 3, waves of matter. Matter can also behave as a wave. This ran counter to the roughly 30 years of experiments showing that matter, such as electron, exists as particles. Since the discovery of the electron in 1896, evidence that all matter existed in the form of particles was slowly building. Still, the demonstration of light's wave-particle duality made scientists question whether matter was limited to acting only as particles. Perhaps wave-particle duality could ring true for matter as well. Louis de Broglie in 1924 used the equations of Einstein's theory of special relativity to show that the particles can exhibit wave-like characteristics and that waves can exhibit particle-like characteristics. Applying de Broglie's reasoning to explain how electron whizzed around in atoms, that is a phenomena which was unexplainable using the classical mechanics, two physicists independently developed two mechanics describing the behavior of matter waves. Matrix mechanics by Werner Heisenberg teaming with Max Born and Pascal Jordan, and wave mechanics by Erwin Schrodinger in 1926. Schrodinger showed that these two approaches were equivalent, though Swiss physicist Wolfgang Pauli sent an unpublished result to Jordan showing that matrix mechanics was more complex. Replacing the Rutherford-Bohr model, Heisenberg-Schrodinger model was established as the true model of the atom, in which we lost the particle essence of the electron. It became a cloud floating around the nucleus. The Heisenberg-Schrodinger model also put a restriction that, quote unquote, the ends of the electron waves must join, a boundary condition. This imposition of the boundary conditions has restricted the energy to discrete values. A consequence of this stipulation is that only whole numbers of crests and troughs are allowed, which explains why some properties are quantized. In the Heisenberg-Schrodinger model of the atom, electrons obey a wave function and occupy orbitals rather than orbits. Unlike the circular orbits of Rutherford-Bohr model, atomic orbitals have a variety of shapes ranging from spheres to dumbbells to daisies. In 1927, Walter Heitler and Fritz London further developed wave mechanics to show how atomic orbitals could combine to form molecular orbitals, effectively showing why atoms bond to one another to form molecules. This was yet another problem that had been unsolvable using the math of classical mechanics. These insights gave rise to the field of quantum chemistry. Also in 1927, Heisenberg made another major contribution to quantum physics. He reasoned that since matter acts as a wave, Some properties, such as an electron's position and speed, are complementary, meaning there is a limit which is related to Planck's constant to how well the precision of each property can be known, under what would come to be called Heisenberg's uncertainty principle. It was reasoned that the more precisely an electron's position is known, the less precisely its speed can be known, and vice versa. This uncertainty principle applies to everyday size objects as well, but is not noticeable because of the lack of precision is extraordinarily tiny. Matter particle has wave nature. So sometimes it is a wave, and any wave can be represented as a function of space and time. So particles or the state of a particle can be represented by a mathematical function. According to Max Born, the wave function representing the particle has no physical meaning, but when it is squared, it gives the probability of finding the particle at a given position and time. Niels Bohr showed that the solution of Schrodinger equation satisfies the equation of continuity of classical fluid dynamics, wherein the wave function is represented as the probability density. The probability density allows us to predict the outcome of a physical measurement. This interpretation, which is famously known as Copenhagen interpretation, had very profound implications on the nature of reality discussed by Schrodinger, Einstein, and many more scientists in the later period. In 1927, Paul Dirac published an excellent paper in which he made a union of quantum mechanics and special relativity and explained the spin magnetic moment of electrons. He, along with Richard Feynman, later developed quantum field theory, or QFT, by using the understandings of electric and magnetic fields. The infinity, quote unquote, infinity roadblock in QFT arising out of electron self-energy and vacuum polarization was solved by Hans Bethe in 1947 by introducing a revolutionary mathematical method called renormalization. Since the breakthrough of renormalization, QFT has served as a foundation for developing quantum theories about the four fundamental forces of nature: electromagnetism, the weak nuclear force, the strong nuclear force, and gravity. The first insight provided by QFT was a quantum description of electromagnetism through quantum electrodynamics, or QED, during the late 1940s and early 1950s. Next was a quantum description of the weak nuclear force, which was unified with electromagnetism by Abdus Salam, Sheldon Glashow, and Steven Weinberg to build electroweak theory, EWT, throughout the 1960s. Finally came a quantum treatment of the strong nuclear force using quantum chromodynamics, QCD, in the 1960s and 1970s, describing the strong interaction as an exchange of gluons between the quarks. The asymptotic freedom of QCD was discovered by David Gross, Frank Wilczek, and David Politzer in 1973, which brought them the Nobel Prize in Physics in 2004. The theories of QED, EWT, and QCD together form the basis of the standard model of particle physics. Unfortunately, QFT has yet to produce a quantum theory of gravity. That quest continues today in the studies of string theory and loop quantum gravity. So with this short historical background in quantum physics, let us understand the importance of computing in physics learning, physics learning and research. Physics is said to be a difficult subject. Physics learning is not an easy task. There is strong evidence all over the world that physics students are not learning the brilliant gifts of science, having characteristics of speed, accuracy, reliability, and integrity. It can execute over 1,000,000 instructions per second without any mistake. It can carry our calculation in just a few minutes that would require months if carried out manually. The computational techniques have provided a friend and servant to science, technology, and industry. In the present learning process, computers are being used for enhancing physics learning also. They can be used to analyze and visualize data, communicate results, run experiments, and monitor equipment. Computing can play an important and varied role in advancing physics learning. We point out the role of computational techniques, namely simulations, multimedia, virtual reality, telematics, and computer-based labs, which may deal with those difficulties and increase the learning process. Some good computer programs for learning physics exist. Emergent computational tools and new development in learning theories have contributed to change in education. But we are still in the middle of change process. The main objective of this webinar is to discuss the role of computation to understand physics and strengthen science and technology. The Python programming language is an excellent choice for learning, teaching, or doing computational physics. It is a well-designed, modern programming language that is simultaneously easy to learn and very powerful. It includes a range of features tailored for scientific computing, including features of handling vectors, inverting and diagonalizing matrices, performing Fourier transform, making graphs, and creating 3D graphics. Python was developed by Guido van Rossum in the late 80s and early 90s at the National Research Institute of Mathematics and Computer Science in the Netherlands. It has been derived from many languages like ABC, Modular 3, C, C++, Algol 68, Smalltalk, Unix, many, and other scripting languages. Now, why is it called Python? G.V. Rossum released Python in February 1991. At that time, he was also reading the published scripts from the book Monty Python's Flying Circus, a BBC comedy series from the 1970s. Rossum wanted a name that was short, unique, and slightly mysterious. Since he was a fan of the show, he thought Python would be the perfect name for the new language. So it has many applications in the fields of embedded scripting, 3D software like Maya, web development like Google App Engine, GUI-based desktop applications like PyQt, PyGTK, image processing and graphic design applications like GIMP, Blender, 3D Max, Maya, scientific and computational applications like SciPy, NumPy, etc. Games like Civilization 4, Vega Strike, etc. Enterprise and business applications, operating system like Linux installers, language development like Cobra, Apple's Swift, etc. Prototyping, network programming, FTP, IMAP, and teaching. So Python is widely used in quantum computing too. Learning Python well increases job prospect also. So, having said these words, let us listen to our honorable guest speaker, Dr. Avijit Kar Gupta, And for that, I announce the session open. Thank you.
Thank you, Principal Sir, for your kind remarks and interesting introduction. Now, I would like to invite Dr. Prakamoy Pal, the coordinator of Internal Quality Assurance Cell, to deliver the welcome address. Please, Prakamoy Pal, sir.
Thank you, Barnali. Am I audible?
Yes, you are audible.
Thank you, Barnali, and also my colleagues of the Department of Physics for inviting me to deliver the welcome address. A very good afternoon. At first, I am much glad to welcome you all to this webinar on my behalf and on behalf of our entire Fakir Chand College family. As you all know, that today's webinar is organized by our Department of Physics in collaboration with the IQAC of the college. Today, our distinguished speaker is Dr. Avijit Kar Gupta, Associate Professor, Department of Physics, Panskura Banamali College. We are honored to cordially welcome you, sir. The topic of today's discussion is quantum mechanics with Python. Our principal sir has given a very lucid and informative introduction on the topic. Actually, this is his parent subject of study, but I am not a person of this field. I shall tell only a few words here. What little I have comprehended is that Python is a multi-paradigm programming language. Its design philosophy emphasizes code readability with its notable use of significant indentation. Its language constructs as well as its object-oriented approach aim to help programmers write clear logical code for small and large-scale projects. On the other hand, quantum mechanics is a fundamental theory in physics that provides a description of the physical properties of nature at the scale of atoms and subatomic particles. Quantum mechanics differs from classical physics in that energy, momentum, angular momentum, and other quantities of a bound system are restricted to discrete values. It is quantization. Objects have characteristics of both particles and waves, the wave-particle duality. And there is limits to how accurately the value of a physical quantity can be predicted prior to its measurement, given a complete set of initial conditions. That is the very famous Heisenberg's uncertainty principle. Now, today before coming here, when I was searching the subject in Google, I found that Quantum Toolbox in Python is an open source software for simulating the dynamics of open quantum systems. It aims to provide user-friendly and efficient numerical simulations of a wide variety of Hamiltonians, including those with arbitrary time dependence commonly found in a wide range of physical applications, such as quantum optics, trapped ion superconducting circuits, and quantum nanomechanical resonators. The software is freely available for use and modification on all major OS platforms. Being free of any licensing fee, Quantum Toolbox in Python is ideal for exploring quantum mechanics and dynamics in the classroom. So with these few words, I think I should stop here without any further ado, as I know that all of you are eagerly waiting to hear from our honored guest, who is an expert in this field. Before I stop, I once again welcoming you all to our present program. Thank you very much.
Thank you, Dr. Proggamay Pal, for your kind word. Finally, I will formally introduce our speaker to audience. Although I believe that we are already familiar with his name, as his book on Python is an essential document for every Python learner. Please welcome our resource person, Dr. Avijit Kar Gupta. I already mentioned our speaker is an associate professor, Department of Physics, Panskura Banamali College, West Bengal. He graduated from Presidency College, now it is Presidency University, Kolkata, and he obtained his MSc degree from University of Calcutta. He did his PhD from Shaha Institute of Nuclear Physics. He also worked at the Institute of Mathematical Sciences, Chennai, and Raman Research Institute as a postdoctoral fellow. His current research interest includes computational physics and interdisciplinary application of statistical physics. Now, I should not elongate my speech and keep the audience waiting. So, I will request our honorable speaker to start his session. Dr. Avijit Kar Gupta, please.
Okay. Thank you, Barnali Madam, for sweet introduction on me. Let me thank you, Principal Sir Shomen Babu, and the IQAC Chairman Proggamay Babu for giving such nice introductions on things. Particularly, Principal Sir gave a very nice overview of all the things connecting together: quantum mechanics, computation, Python, and everything. And I believe this speech will be very useful for beginners and students who are always learning. We are all always learning. Good afternoon, everyone. For a moment, I am speaking from my mobile phone because I'll switch off this and go over to my laptop, because my laptop, this camera is not working. Otherwise, everything is fine. So, I will not waste much time. I'll just stick to basics, particularly how we can solve various problems, particularly Schrodinger equations of various kinds and for various problems in quantum mechanics is by numerical methods with Python. Okay, so let me now put this off. Let me also thank all the people coming here to listen this, the students and teachers of this college. Thanks, Manoj, for taking all the trouble to contacting me all the time. And my good friend Shodmila is also there. And thanks to all other students and teachers coming from various colleges. So let me stop here and I'll connect to the laptop. It will be an interruption of a few seconds, I think. Thank you. Okay, I think I'm back. Yeah, I'm audible. Can you please?
Yes, sir.
Okay. Good. So I begin my what I wanted to say. I'll for the students, I will stick to very basic, and I don't know how far I can go in a limited time because. But the book is there. I have written quite an aspect of quantum mechanics for various problems. But the experienced people here attending this lecture who will be wanting to know very difficult problems, how to solve very many difficult problems, we can discuss later. Even I also am learning everything day by day, every day. Okay, so we can discuss more difficult problems later on.
I'll stick to very, very basic particularly for the beginners and students. Okay, let me share my screen. Well, I think now soon you will see my screen. Okay. I hope you can see my screen. Okay, so let me first talk about what we are going to do. We are going to solve some problems in quantum mechanics. So that's why the title is Quantum Mechanics. And obviously this part is a part of numerical method, some numerical method. And we'll solve these problems. We'll write the codes in Python. And we'll use the technologies, all the machineries of Python. I hope the students particularly are well versed with Python by now. They know how to write a code in Python given an algorithm. I hope people can understand the magic of the arrays, how the arrays can be manipulated, and can be and the very minimal programs, amount of lines can be spent to write a very nice program, an efficient program in Python. Okay, and I'll base my lecture on these technologies. But before I go, let me talk about what we do here today. The quantum mechanics, basically what we'll solve is numerically we'll solve Schrodinger equations. So we'll solve Schrodinger equations. It can be in 1D, it can be in many dimensions, but to be simple, we will work in 1D only. But in 1D, there are time-dependent Schrodinger equations you have solved analytically with very many different kinds of potentials, harmonic oscillator, infinite square wave potential, hydrogen atom problem, and so on. And also there is time-dependent Schrodinger equation which sees the evolution of the wave function. That means it is a partial differential. So time-dependent Schrodinger equation is basically a partial differential equation. And I believe you have spent quite a lot of time in solving partial differential equation in third semester or fourth semester, I guess. Okay, so you already know how partial differential equations are solved. And to tell you, it is not an easy job. Actually, for a particular problem, given the situation, it is easy. I mean, you can solve it. But people who work in partial differential equations, they know it very every day from their work, that managing a partial differential equation numerically is a very, very difficult task. The main reason is there are various partial quantities are involved. And when you solve them by discretizing the differentials, partial differentials, through finite the finite difference method that you already know, but I will introduce that. So there are various kinds of instabilities. There are various kinds of technicalities involved, so that you will not easily get the answer that you want. Okay, so we'll solve some very simple problems only. So the time-dependent Schrodinger equation, you will have del psi del t, right? So the first order differential of, with time, and then you will have del 2 psi del x square, even if you want to be in 1D. And for 2D, 3D, you have other differentials. So there are two kinds of differentials, first order and the second order, and obviously psi is a function of x and t. We'll go there, we'll manage that, how we solve partial differential equations. We'll see that. We'll see scattering and all kinds of animations if possible today. And other thing is that you solve also some stationary solutions. That means del psi del t equal to 0. That means you solve some stationary solutions, And when you solve a stationary solutions, when you solve a stationary Schrodinger equation in 1D, say, this becomes from PDE, this goes directly as ODE. That means you have no time dependent, you have only, that means del 2 psi del x square is, you can write it as d2 psi dx square. Okay, and psi is a function of x only, right? So then you think, well, you know how to solve a ordinary differential equation, because ordinary differential equation you have learned in your third sem or so, that you solve it by Euler method, solve it by Runge-Kutta method, or any other methods. So you know that. So it is easy then. But no, there is little more problem because it is quantum mechanics. When you solve these problems, there you have to understand the solution is not acceptable for all the parameter values like energy. So you solve it for, as principal sir was mentioning, and you solve it for specific values of energy E. That means, there comes that energy is quantized, and those are the Eigen Energies. So basically, you have an one ODE plus the problem is now a little different, and this is with Eigen Energy. Okay, and no, the trouble is not already over. In ordinary differential equation, the most of the ordinary differential equations through Euler or through Runge-Kutta or whatever, you have also used this function ODInt. Today I will use this function from NumPy or SciPy. It is in SciPy. So you can use this as a black box. You give the function name, you give the dependent variable initial value and the array of the independent variable, and you can solve it automatically. The solution is ready for you. You don't have to even think how it solves. Okay, so you will use that to do it in a quicker way. And of course, when you solve production quality work, when you do production quality work for your research and things like that, you will not write exactly a program to solve by Runge-Kutta or Euler, etc., etc. But those things you should learn, and that's, I believe you have learned, because those are important for you to know how you solve a ordinary differential equation. But remember, those problems where we have solved, those problems are ordinary problems, those we have solved already, those are initial value problems. So initial value problems are what? Initial value problems. You have learned them in your mathematical methods course. The problems you solve mostly, those are initial value problems, IVP. Initial value problem means, for example, suppose you have a differential equation, dy dx is a function of, it can be x and y both. So it's a simple, y is a function of x, of course. See, this is a form of a ordinary differential equation in 1D. And if it is an initial value problem, you have to solve it from some starting point. Suppose you start from some point here. So you know at x0, what is your y? You call it y0. And therefrom you build up, you solve it, discretize this through Euler or Runge-Kutta, and you build up step by step and go to solve some problem. Suppose the then solution finally looks like this or something like that. So that means you have some y at x0. X0 is the initial value, initial point, right? Here from you start, and suppose it is y0, say. Often we start from 0. Okay, so this is the initial condition. So for a 1D, for a first order ODE, you have one initial condition. Suppose you have a second order ODE. Suppose you have, it is first order. This is first order. Suppose you have second order ODE. And obviously you will have something like this, d2y dx square will be something, will be here something, but rather I talk about a real second order differential equation and tell you how to, and remind you how we solve it. For example, we solve a differential equation, very well known differential equation, d2y dx square plus lambda dy dx plus ky equal to let us say 0. That means it is a damped harmonic motion, not forced. Right side is for the time being it is 0. It's a homogeneous equation. How do you solve it in computer? Because computer, you know, this your ODEs, your ODE solvers, Runge-Kutta or whatever, and or ODE function can solve only first order differential equations. So you make this split this second order differential equation into two first order equations. So you can think, okay, my dy dx, for example, suppose better for you, I write it as d2y dt square, say time. So that makes more sense to you at the moment. So it is a damping term. This is acceleration, and of course this is restoring force. And so dy dx, you call it, say it is your velocity. So you introduce another variable v. Sorry, d2 dy dt. So y is your displacement, t is your time, so this is your velocity. So now the equation you can write dv dt, and on the right side you write minus lambda v minus kv. So what happens is that you have two first order coupled ordinary differential equations, and each of them you solve with Runge-Kutta or whatever, or your ODE solver. And you know here they are coupled because here you have v, here you have this and this. But anyway, now you have, instead of one variable, you have now two variables. One is y and another is v. An independent variable is t, and you have now two dependent variables. So to solve it, you have to know at t0, that means at the initial time t0, what is yt0? It may be y0. And you have to also know what is v at t0. That means initial position and initial velocity. So you have to tell something. So with that two things, you start solving, and you can now solve it. So this is initial value problem. Of course, this is second order differential equation. And for the second order differential equation, you need two initial conditions. But you see, in quantum mechanics, the problem is little bit something different. Because in quantum mechanics, you have the problem, it is called boundary value problem. So quantum mechanical Schrodinger equations that you deal with. So the Schrodinger equation, that first thing you have to understand, that equations are basically boundary value problems. Because you understand, suppose you have an infinite potential box, say you have a box, and you know this is an infinite wall, and particle is trapped forever here, so particle cannot escape. So you know here it is, say it is x-axis, so here it is say 0, and on here it is say length L. So within that, particle will be there, and the whatever wave function, whatever it is, it should be 0 here, it should be 0 here. So if it is at the if it in the ground state, you know you have solved its maximum here and the 0 here. So at the two sides you are sure that should be 0. If you have other these things, you have other kinds of solutions for other higher energy levels. Whatever it is inside, you will know the two sides are known and the two boundaries are known. So you can, before you solve the problem, you begin with this idea that the answer at the two boundaries are known. So that this kind of problems are called boundary value problems. Perhaps we have not done much, we have not solved many boundary value problems in mathematical methods, or we have solved, but we mostly concentrated on initial value problems. And in Python also so far we did that. But now we have to solve stationary 1D Schrodinger equation, that is ordinary Schrodinger equation. One difference is that the parameter involved here, constant parameter, that is energy E, that is not something arbitrary, that has a fixed value for which the solution is possible. You have to find that one. And the next is the problem itself. When you begin to solve, the problem is a boundary value problem. Okay, you have to understand that. So suppose you have a harmonic oscillator. Its walls are not rigid that way. So here also you can understand, but the two ends are not infinity. It goes on forever. Only infinity at infinity only. But you can, from physical reasoning, you can, and now you know the solutions also, the wave functions may come out. Wave functions may come out. The tails may come out of this well, but somewhere, little away from the well, somewhere it has to be 0. So you can think this is your boundary. Here you know at some large distance it is 0, and some large distance it is 0. So whatever problem in quantum mechanics you take, whatever potential well you take, for the stationary state, for the 1D stationary time independent Schrodinger equation you solve, even it looks very, very simple, but it has the two things in it that you have to consider. First, it is a boundary value problem, and second is the Eigen Energy problem. So how do you approach a boundary value problem? So let me tell you how we solve any arbitrary differential equation where there is no Eigen energy kind of thing. For any arbitrary kind of second order differential equations, basically the philosophy is this. So this is the philosophy. So how basically, but before I go to state you the philosophy of something, let me tell you that the problems can be, the solutions we do in two different ways. Solutions of these quantum mechanical problems. One problem is understanding this is a boundary value problem. We solve through a method which is called shooting method. I'm going to tell you what is shooting method is. It is shooting method, and another method is finite difference method. That means I told you the any finite difference method you can apply to any partial or non-partial ordinary differential equation, doesn't matter. Okay, you only discretize the with the finite difference, expand the terms in Taylor series, keep up to some terms, and then you discrete. That is a discretization formula, and you arrive at ultimately at a recursion formula or something like algebraic equation. Because computer does not understand calculus, computer understands only some elementary plus minus division and multiplication. That means algebra. Okay, so it's the two methods you can solve by two methods. Finite difference method. This is both of the subjects are they can go very deep. If you study shooting method, you can go on spending some time of your life to analyze various kinds of shooting methods. If you can muster over this finite difference method, this is very, very useful for all engineering students. They solve these problems in these finite difference methods. I have seen mechanical engineering and other electrical engineering people, they solve very many different kinds of differential equations through finite difference method. Any good mathematical methods book contain this. Okay, so either shooting method or finite difference method. We'll show both. And then if you apply finite difference method, then there are also two kinds. That means by finite difference method, you have arrived at a algebraic formula. You have arrived at an algebraic recursive formula. That means you know values for certain n. You can know for n plus 1. You can know plus n plus 2, and so on. Those are called recursive formula. Those type of formulas. But you can cast the equation in such a form that it looks that you give some values and you can iterate and find out the next values, and so on. Grossly, they are called explicit method. That means you solve the algebraic equations under a for loop. So it is called explicit method. We can solve it solving the recursion relations. And the other method is you can construct the matrices. So you can call it a matrix method. So all we'll try to touch today, but I don't know how deeply I can go, how technically, how detailed I can talk about today. But let me give an example for first shooting method. So what is the philosophy of shooting method? Shooting is shooting. If you have your experience of shooting something, suppose you are in college NCC or some have played with your this called gulti in your childhood. So philosophy of shooting method. First understand that. Okay, the basic idea of doing any kind of computation is to understand the philosophy behind it, understand the how it is done, and then the arrive at the some steps which are called algorithm, step by step. And once you are done, then the rest is easy. You can write this, explain this, you can rewrite this algorithm in terms of its any computer language, be it Python or Fortran or C or C++, whatever. But those part is, to my view, those parts are not that difficult. Main difficult thing is to understand the algorithm. I have seen also with my own life, and also I am seeing the students, they are not very careful about the understanding the algorithm. Algorithm is the most important part of anything. Okay, so anyway, so let me in short talk about the shooting method. Suppose you are going to solve a problem. You know here is your x0, and for x0 you have one initial conditions. You are solving a boundary value problem. You are solving a boundary value problem by shooting method. So what you have known at x0 some value. This is y, this is x, and here at other end, suppose this is x1, for example, here is x0, and the other end, you know something, the value is y1, right? Here it is y1, here it is y0. So at x0, the value is y0, at x1 is y1. Those are two boundaries, right? This is one boundary, this is one boundary. And those two are given for a boundary value problem. You have to start, but you have to start from here. Remember, when we discretized, when we split the damping, force damping harmonic motion into two parts. One was position or displacement, another was velocity. So you have to know position, you have to know velocity. And you know velocity is basically dy dt. That means a gradient, right? That means a derivative. That means similarly you want to start from here, but it is not here. It is not given. You have given only one initial condition here and another initial, you will not call it initial condition. Now this initial condition is boundary condition on side and the boundary condition on the other side. You will go from here to here, but which path you will follow? Suppose here you are standing, you want to shoot here. How do you shoot? Will you shoot from here and it will go here? Will you shoot from here and it will go here? Will you shoot from here and it will go here? You do not know. You have to give it a trial. So if either in direction or this direction or this direction or this direction and so on, you do not know. Suppose arbitrarily you shoot from here and in this direction, that means initial slope is there. From the guess value, you guess something and you see target is here. You reach, probably it is too much. Often you see in the Euro Cup, the goalkeepers, they try to shoot in the goal, but sometimes the goals, most of the times, they cannot aim that close unless it is a Ronaldo or Messi or someone. So they often shot in a certain way that it goes above, or sometimes it goes in this direction. Suppose you start with this guess value, these go far beyond this here. So you know now your target was here and you end here. Then you start another. Suppose now you say, okay, I will not give this high initial velocity or the high direction. My direction may be something like this. So I give this direction now. So it may be here that it goes down here. So it is called overshooting. So it is called overshooting. And this you can call undershooting. This is called undershooting. So now from the two instances, either you go, it may happen that in one shot you can shot here. That is a special case. It may happen that on the two times you are go here and go here also. Another time you could go here also. Another time it could here also. That means from the two initial values, this is the initial guess, this velocity, and this is the initial guess, quote unquote velocity. With the two initial values, you have the two guesses. One may have come here, one may have arrived here. It may be, both may be undershooting, both may be overshooting, one may be overshooting, one may be undershooting, doesn't matter. But it is more, it's better if you try to hit in such a way that one is overshooting and one is undershooting. That is for technical purpose, that is for numerical purpose. It happens. You will discover that. Okay. And then you have the two values here and here. You employ these two values and two slopes, and you do write this kind of formula. That means that is your guide. So next time with these two shots, missed shots, and with these two initial values, etc., you may construct some kind of formula, some interpolation kind of formula, and that will guide you better and better and better. You go on shooting. Sometimes here, sometimes here, sometimes here. Maybe after 100 attempts, you actually arrive at a solution. So that is your basically shooting method, which you apply for a boundary value problem. I think the example. Okay, let me think of the algorithm. When you think of the algorithm, so what we'll do? The story I have told you now, the algorithm is this. Now, if I write point by points in a short way, so you have some y at x0, this is y0, this is given. Remember, one condition is given, right? And you say, for example, another variable is z, for example, either you use v or z, okay? Say I am using it, the z. So that z is x0, you call it something. Say something, say I call it, I intentionally write one z1. That's reason will be clear now. Z1, it's a guess value. This is guess value. You do whatever you like. You can have an intelligent guess and so on. This is first guess value. And the second, you will start with another two these things, yx0 equal to y0, that is given. And z of another x0 will be another z2. That is second guess value. Second, this is the first guess value. This is the second guess value. Now you have two sets of, you can think this is one set of initial condition. That means you can solve it by Runge-Kutta now. Even if it is boundary value problem, because you have the liberty, you have these two initial conditions. Although one is guessed, another is given. And also another one, you need two. Then you can think for the third attempt. This is first attempt, second attempt. This is the third attempt. This is the third attempt. You don't guess another. You just calculate from these two values. Okay. You have to. You can always construct a straight line from the 2 points, of course. So you write some next guess value z3 equal to z2 plus z2 Z2 minus Z1 into the other end is, I called it Y1. The other is, this is Y0 and other end is Y1. So I am using this. You can write how far the third attempt will be closer to Y1. So you can write it as Y1 minus what is, I write it as W2. I'm writing it what is W2 and W1. You can guess. And this is W2 minus W1. Let me call this, say this is W1, this solution, okay? This overshooting solution, and the undershooting solution is W2. That means you see immediately that Z3 minus Z2 by Z2 minus Z1 equal to Y1 minus, the actual solution minus one flux solution, second solution, by second solution minus first solution. That means basically you have one Z1 is the guess value. Sorry. That means you have one, you can think of this way, you have one Z1 guess value, and for that solution you obtain W1, and another guess Z2, and this solution you obtain W2, but from that you want to have third. So as if you have 2 points, and it is an equation of a straight line between the 2 points, okay? And you can also understand that this is basically an interpolation formula. You have done Lagrange interpolation formula. If you have only 2 points and you can write the Lagrange, you go back to Lagrange interpolation formula, you will see the Lagrange interpolation formula looks different, little different, but you can manipulate these terms and recast it in Lagrange interpolation formula. But basically that is a straight line. So basically this is the guideline. This guideline will take you, will tell you what will be the third value. And then again replace Z1 by Z2, Z2 by Z3, and you will have Z4 and so on. That means you have to iterate these steps inside a for loop. Okay, so this is the prescription. And number 4 is iterate number 3 points over a loop until accuracy, until some accuracy level you want to achieve. Okay, so you can think this 1, 2, 3, 4. These 4, of course, you have to solve it. You can write it's okay. You can write it's okay. Something you have to solve it, but that is trivial. Okay, basically these will form the algorithm. Now let me solve a very trivial problem other than quantum mechanics, and I will tell you how this is working. Quickly, I will type the equation for you and will solve it if you have patience. So, for example, I chose one in my book. Also, I chose one very nice problem: y double prime equal to minus y plus 2 of y prime square by y is a between a standard textbook problem in mathematical methods, and the solutions are y minus 1 equal to y1. That means at x equal to minus 1 and at x equal to 1, both the solutions are incidentally equal, and they are 1 by e plus 1 by e to the power minus 1, which is 0.32403 something. Okay, and how to solve? That means how to solve? You have to write, say, y prime equal to, now I write it in general, z. Okay, so it's a function of, first function of x, y, z, and then I write, say, z prime. That means here it is z prime, and on the right side it is minus y and plus 2 into z square by y. So you call it another function, second function. In principle, it is a function of x, y, and z. So it is equation 1 and equation 2. And the exact solution also we know. That's why I'm interested in. I'll match it with. But remember, this is not yet quantum mechanics. So I want to describe these once for all to the beginners or the students, so that you learn how to solve any ordinary differential equation boundary value problem in quantum mechanics, in computer. So yx is 1 by, you can guess the solution, e to the power x plus e to the power minus x. You can understand, because if you write x equal to 1, you will have this. If you write x equal to minus 1, you will have this. So the two sides are symmetric. That means you are expecting that here it is a, say here it is, I should not write this. I should say here it is a minus 1, and here it is a plus 1. And see, this is the x-axis. And so suppose this is 0.32 something something. Here it is, and here also 0.32 something something. So the solution at -1 and solution at +1 unknown. Okay, how it will go from here to here? What will be the nature of this curve, this trajectory? So that is, we have to find out. That means that is the solution. Okay, so let me actually, based on this the previous algorithm, previous set of algorithms. So what are those? I first will choose two guess values. Then I will think of this guiding principle. I have to have some guide. So this is my guide. For the third value, I can construct from these two first guess values, and then so on, go on and go on until I reach some accuracy. And then of course I will solve through some standard ODE solver. So let me go to the computer now. Okay, so let me now demonstrate. Well, let me go to, go to something. For today, I'll show you in Anaconda Jupyter notebook. If you have not seen it, it's no problem. But if your machine permits, you may download this Anaconda. You can see this Anaconda navigator, all free, but it takes little more space than usual Python idles. But this is very nice. It's very fancy because you will feel the comfort of working here. Particularly people working in machine learning and data science, they love this Anaconda. And this Jupyter is called Jupyter notebook. Well, let me begin to write a code for you. Okay, although writing a code is not something very kind of something which you can take much pride on this, because code, anybody can write a code, and everybody's code should be different, because you think understanding algorithm is the most important part. Okay, so let me write import numpy as np. This is essential for your import, and we will need some ODE solver. So from scipy dot integrate import ODE int. This part you know, and I run it. It doesn't say anything. That means it good. Now I will write this to. I will write this to these things. This. I'll write these things. I have one function, I have another function, and to solve with ODE int, you have to combine these two functions into single function, because it takes only in that form, right? So you can write, so I can define a function where I write, okay, u comma x, and I will know that inside u there will be two parts, y and z, right? That means it is the structure of the ODE int that they have designed, how they demand that. Okay, because now I write y comma z equal to u. That means you have got something through u as an argument, and inside u there are two parts. First is y, and then second is z, and you very well know this is called unpacking. We'll pack two things in u, and then we'll unpack here yz equal to u, and then you write f1 and f2, two functions. The first function is z, and the second function is, because the first function f1 xyz is basically z, right? and the second is minus y, and the plus 2 star, and then z star square, and then by y. So 2 functions are done, and I'll return these 2 functions in the packing form, f1 comma f2. It's a list of 2 functions. So it's done. So next is I have to define the domain of x. Basically, I will use np.lin space. You know, it creates linear space, and I'll create. I want to see the solution between -1 and +1, because you have known that you have already know this. The solution I want to define. I want to have the solution between -1 and +1. So, so this is -1 +1, and say I want to take some 100 points inside. In fact, you better write 101 points. So the divisions will be, because the 0 is there inside, so it is 101 points, means the differences are perfect. That doesn't matter. You can write anything. You can give anything. So x is this. And the initial value of y0, that is 1 by np.e plus 1 by np.p. Understand? This is e, and this is e to the power -1, right? So this is basically this will be 0.32, etc. So you can see also. You can see also. So it is 0.324 something. Okay. Well, and now you can give z1 and z2. These z1 and z2, as we used in this algorithm, these 2 are basically 2 guess values. 2 guess values. You can see it, give 1 guess value and see the answer. You can give another guess value and see the answer, right? So I have seen that for quite some time. You can also do this experiment. I will not go into very detail today because everything is not possible to tell at this short time. But well, I saw that for 0.1 and 0.2 or 0.3, if you give 1 guess value 0.1 and then another guess value 0.3, for one is overshooting, and then for another it will be undershooting. Either of this. So within this range, one is one overshooting and one is undershooting, and so if you try to guess the third, try to calculate the third guess value and then fourth and fifth and so on, the process will be quicker if you start from any such direction. Okay, so these are the 2 guess values. Done. Next, you give the 2 initial conditions. What are the initial conditions? You give y0, right? Y0 is here. This is one initial condition. And what will be another initial condition? Z1, right? You have given it 0.1. So I have combined them. I have packed them in U, right? And now there is nothing. They have to solve. What is the solution? Solution is OD int, right? And what you give, the function name, then U is this thing, 2 initial. Actually, you should write it's U0 if you want it. U, and then you have to give the X, this thing, right? And then the X array, complete domain, okay? And so this is the solution. And what will be the end point of the solution, right? What you want to know, you want the solution. You have got the solution, but you want to reach here. You see, this is with Z1, and this is your entire thing is your solution, but you want only the last value. This is very important. Remember, I don't want everything. I want only the last value for my testing, whether how far this is from the actual bull's eye, right? So, basically we call it W1. We called it the W1. So W1 is solution, and this is the colon comma 0. That means all rows, and the 0th column. That means the first column, basically. Okay. So that is for your solution. Basically, the solution for Y, right? So that is your solution. If you write it 1, that will be solution for actual Z. Okay. This solution and its last value. Last value is for the entire, this is basically a numpy array, right? If we write it as -1, that is the last value. So that's your W1. Done. Similarly, we'll call it for a second guess value and so on. But since we will be doing for in a loop, we'll do that inside a loop. I'll give a tolerance value. That means how far it is from the actual value. So that it will decide. So tolerance equal to, I say, well, it is 0.001 or something. Okay, let me give this tolerance value. That means accuracy level we set. Now I write for I in range 1000, say for example. Okay, so now I now write what? Now this is the first, we took the first guess value and we got the first solution. I don't know whether it is undershooting or overshooting, hardly matters. We checked actually, but at the moment it doesn't matter. But inside the loop, this is technicality. You write for another guess value y0 and z2, say for example. And then again the same thing, solution equal to OD int, the same steps. You could put them inside again another function, etc., etc. You could always do that. Do this, and the W2 is actually solution and then colon, comma 0 and -1. That's it. So W2 is done. Well, and then now I will compare. Now if I will compare absolute value of W2 minus W1. So the difference between two results with the first guess value and with the second guess value. I am at the moment not seeing where it hits and so on. I just want to check because suppose we have seen that before. Okay, so if this is less than tolerance, okay, if this is less than tolerance, then I'll say okay. You can write, I can break, then break away. Okay. Okay. Now, well, now I write. Otherwise, what will happen? Otherwise, the loop will continue. Only this condition is given. The difference between two successive these values results. If it is less than tolerance, then only break away. Otherwise, it will continue. Okay. So let's see that. Now Z1 comma Z2 equal to Z2 comma Z2, that algorithm, right? Z2 plus Z2 minus Z1, right? And star, right? Y1 minus W2 and by, let's see the formula you had written, W2 minus W1. This is this. This thing will be renewed as, I'm sorry. This is Z1, Z2 and equal to Z2, Z3. That means earlier Z2 will be now Z1 and this thing Z2 plus something updated Z2, which I will call Z3, which is now Z2. I have not written it Z3, but you understand this is Z3. Well, this is Y1. I call it, because Y1, okay, let me write Y1 equal to Y0. Both are same. Okay, so now I call it Y1. Okay, done. This is done. And also, when the loop goes back, it will also understand W1. The next time the W1 will be W2. These are just updating. So I update Z's, I update W's. That's it, done. So now you run this. You will see the magic. Y1 is I have not actually after putting this I have not actually run it. You have to run this, right? I run it everything again. I run everything again. I run Baro Taro. No. So yeah. So now you done. Work is done. In Python Jupyter, when you see this number is coming, before that it will be some star or something. That means the program is working. When the number is coming, that means you will know that the program is done already. Solved. Now I will plot. So import matplotlib.pyplot as PLP. and PLT dot plot and X versus the final solution. Now I will plot the final solution. Final after these loops, every time it is finding the solutions, right? Every time it is finding the solutions through ODINT. So it doesn't matter. The last solution it will create. So colon, comma, 0, because I'll now plot the entire solution, right? So that's it. So this is it. And well, I can plot it. I can plot it with Golla, that is bullet, and also to make you believe, I will also plot the exact solution x comma 1 by np.exp x, right, and plus np.exp minus x. So okay, so I think it is okay. Okay, no, not okay. This is these two brackets, and we need another bracket. I think now it's okay, right? This bracket, oh, these two brackets. Oh, sorry. Ah, now it's okay. Okay, and now that means this will be the exact solution. It will plot with a line since I have not said anything, and this will be with bullet points. Okay, now let me plot them. So you can see this solution. You can see exactly on top of each other. So this is the expression of 1 by e to the power x plus 1 by e to the power minus x. The orange continuous line is the exact solution, and the bullet points are the solution I have got through my numerical work. So you've seen that ordinary differential equation, but it's a boundary value problem. How we have solved this? So what is the philosophy? Philosophy is we start from some guess values, 2 guess values, and then we have some guiding rule. This is our guiding rule, some kind of interpolation, because we have nothing to do here rather than thinking of some straight line between 2 sets of points. That way we find the third point and the third attempt, what will be the value for the third attempt and fourth attempt and so on, and then test this accuracy level and inside a loop and can do that. So this is basically the shooting method, but it is up to you. Once the program is with you, you can now check with very many different kinds of Z values and can check how you can, for which one something is overshooting, for which something is undershooting, and so forth. I'm not going to waste more time on this, but let me tell you, in this problem, you can see in my book also, but you can also see that suppose I start from something 0.32 here, I am to reach here 0.32 on the other side. You take one value, say one Z1 value is 0.1, it may go like this here, and for the another it may go like this here, and so on. Say suppose for this is for Z1 or Z2, you just take. It may be Z2 here and Z1. You analyze and I just plot it. Okay, and the original solution should be here. This is the original solution, right? That's what we got. Okay, so this is a ordinary differential equation, but it is nothing to do with quantum mechanics. It is with ordinary differential equation, but boundary value problem. So we have solved it through shooting method. Shooting method means basically you start from guess value, one guess value, you start another guess value. That means 2 sets of initial conditions and try to reach on the other side, try to hit the target. That's what it is. Okay, basically. And this principle will be always there for shooting method. Now we'll solve quantum mechanical problem by shooting method. So what we'll do there? So we'll solve quantum mechanical ODE, I must say. I mean, this is Schrodinger equation, time independent Schrodinger equation in 1D, quantum mechanical ODE in by shooting method. overshooting. What I told you that these quantum mechanical ODEs, that means Schrodinger equation in 1D without time, so they are boundary value problems, but there is one thing extra. What is that extra? And that is a very vital thing. So that is the energy is, this is the Eigen Energy. You think of the Eigen Energy. So this is extra problem. What do you do? No, here the problem is the boon, because this Eigen Energy, now this will guide you like a North Star towards the solution. You don't have to write an interpolation formula, etc., here. Here the life, contrary to what you may think, the life is easier here because you have now Eigen Energy. So you search energy ranges for which Eigen Energy it goes closer, overshooting, undershooting, etc., which goes closer to that. That means we will look for Eigen Energy. We will look, we'll search through energy ranges. How do I know this is Eigen Energy? Okay, so that means Eigen Energy is that energy for which the solution is acceptable. Suppose you are solving a problem here, and you do not know what is Eigen Energy. You try very much different energies. One function like this, one function like this. But for one function, you know 0 here and 0 here. In between, what it will be, that is up to them, up to the equation. I don't have to worry about that thing. So it will be eventually like this, or it will be eventually like this, or it will be eventually like this. So these two, you will accept those energies for which the solution, you check the two ends. Okay, so I will look for the Eigen Energy. I will not consider, again, I don't need, I can do, but that is something that will be something extra that is not necessary. So let me talk about quantum mechanics. So time independent Schrodinger equation in 1D. What is that? Minus h bar square by 2m d2 psi dx square plus vx psi x equal to, this is the person sitting here, Eigen Energy. So this will guide us. Okay, to solve it in computer, this is a perfect second order differential equation. It's a boundary value problem, and otherwise there is no reason to solve not to solve it. But we will, before we solve it, usually what we do, usually there are lots of factors, h cross, m, sometimes there will be electron charge and things like that. All those things we can actually, because we are solving in computer, so we can actually rescale them. So we can always recast the potential sometimes energy, sometimes the equation in such a way that we make them dimensionless. Okay, so here d2 psi dx, so that we don't need to care about dimensions. We can put all those small values of h and h cross and m, but that will be too much, because the computer will always carry all those very, very small numbers, and it will do mistakes, and the errors will accumulate, etc., etc. We don't want that. We can later rescale the energies or whatever with the scale values. So we can call it minus 2m by h bar square, and it is e minus v of x psi. Okay, so usually you see that scaling is you write, you take m and h bar square in such a unit that 2m by h bar square probably is 1. So this is your scaling. That means equation looks even simpler. So equation looks a very trivial equation. It is a very, very trivial equation, d2 psi dx square equal to, say, minus, and to put it minus inside, so it will be vx minus e and psi. So that's your equation. How to solve it? Of course, let me in the language of whatever we had been doing with ODINT. We'll solve this problem with ODINT. So let me, for the time being, let me think that psi is your y. Psi is your y, and of course d psi dy is d psi dx. D psi dx is your z, right? So you write this equation in terms of psi is, remember psi is your y, and d psi dx it is z. So you have to split this equation into two one DOD. That means you write dy dx is actually z, which you call the first function, again like before, x, y, z. And then you call dz dx. So that is your phi of x minus e into y. And here, remember, here energy is constant, but of course phi is dependent on the x domain. It's a function of x. And you call it some function f2. In principle, it is x, y, z. So this is equation 1 and this is equation 2. Now we will solve this in computer. And to solve this, our model is, suppose very first model we encountered in quantum mechanical books is the infinite square well potential. Is infinite square well, we'll take that. So basically Vx equal to 0, and if x is between some 0 to some a or something, and infinity otherwise on two sides. Beyond this range is otherwise. So basically it's a infinite square well potential. And we know the analytic solutions. We know that analytic solutions are energies, Eigen energies are En equal to h bar square pi square by 2m s square and n square. And we know that n equal to 1, 2, 3, 4, and so on. N equal to 1 is the ground state, first excited state, and so on, and this. And if you also if you want, you can put a equal to 1, then it will be again simpler. And also you have understood that 2m by h bar square equal to 1. That means energies should come in as E1 equal to h bar square by 2m. This is 1. A is 1. So basically you will En is pi square n square. So as simple as that. So you have first ground state is basically pi square. So basically 9.87 in arbitrary unit. The first excited state, it is 4 pi square. So this is 39.48. This is the ground, and it is first excited state. So and so on. Why I am telling all those? Because when we'll do the computation, you will see whether this matches with this. Okay, exact solutions. Otherwise, there is no fun in doing. Well, and the boundary conditions, because it is a boundary value problem. So remember, we have taken a equal to 1. That means we have thinking of a domain which is between 0 and 1, and this is infinity, infinity. Okay, so boundary values. So whatever will be your solution, you have to have psi 0 equal to psi 1 should be equal to 0. So these are the boundary conditions. Well, now I will apply shooting method, and what we'll do instead of the guidance by the interpolation formula, I will check the energy values. Okay, so again we'll try from a guess value and then check what it is. Then we'll start from, say for example, again we'll start from the same method. We'll start from here. It is 0. We know the solution is here is 0. We'll start from here one initial value and one guess value for Z, and then we'll see where it reaches. Maybe it reaches here, another maybe it reaches here, another maybe it reaches here. So we'll see what reaches here. Okay, in between will be lots of, and these will be guided by our energy. So let me write a program, and while writing the program, I will tell you quickly what it is actually going to do. So yeah, let me do it here. For the sake of completeness, let me import again everything for you. Import numpy as np. Then from SciPy, please stop me in between if you are got bored. Integrate, import ODINT. You need this ODINT. And also for the normalization of the wave function, I have to integrate later. So I also need sims. You know, those sims is the function which integrates any function, any integrand. It's okay, in a definite integral. And ODINT is ODINT, you know. Okay. And also, I will need one thing that I have not talked about. One thing. I need to a bisection. I mean, as some root finding function. So from SciPy, why I'll explain now. Optimize import bisect. No, we'll not write any program. All the programs are written here. Okay, so this bisect will take care of to find out the root. Why I need to find the root, I'll tell you. And also at the same bunch, I just also import matplotlib.pyplot as PLP. Okay, so it's your quantum mechanics. It's your quantum mechanics in time in the independent and 1D. And let me, yeah, okay. So here. Let me first define the function. Define if now you have u and you have x again. But remember, here we'll do a little trick. That's not trick, but we include the parameter e also, because e is something which is not a fixed value, right? We have to change e and see where the solution goes. So we'll actually change e. So e is something parameter. E is at our hand. Okay. So we'll change e and see the solution. Okay. The constant which we can vary. So that is this. And you write y comma z equal to u. The same unpacking. Then you write f1 comma f2. Then it is first one is z. F1 is z and f2 is just v minus e star y. Remember, I'll tell you v because for infinite potential it is either 0 or nothing, or okay, because it is always 0. So that's why I'm just not writing anything function of x, but still I write v just to show you that the expression looks like v minus e into y. Y means your sin x, your phi x, and return it's your f1 comma f2, right? So run. Good. Now you will now find out. You will now call the ODINT. Inside that you write f. Inside that you write u. Inside that you write x. And inside that, since I am also taking interest in e, so here in ODINT you will see there is a keyword argument called args. Within that args, I can put as many parameters as possible as I want in terms of a tuple. So I write e comma tuple. So it's a tuple. Okay, that means I am incorporating this e inside this. So this gives me a solution for a particular e. Okay, and I can write this as solution simply. You can find you can have U. What is your U? You can have U is some V is of course 0. Let me also write first here. Let me also write create here, and let me also write some V equal to 0, because in the domain I am working V is always 0. So that means it is again looks very trivial equation. Okay. And U is basically you start guess value from first is 0, psi 0 is 0, and the another guess value you don't know, but you start with any small value, doesn't matter, plus or minus. I have checked the final solution will not depend on this guess value, of course, because the entire solution will be hijacked by the energy, correct energy you choose. Okay, so you give you give. I'm sorry. Here can also I write, and you give x also in p dot lin space, and you are solving in between 0 and 1 and give 101 points. I intentionally choose 101 because it starts from 0, so that the differences are something respectable. Okay, and you give so one initial value and one guess value in packing. You give x and you give particular energy, right? So, but I can now give some energy value. I do not know, for example, if I don't search, I can give some energy value, and I can now calculate this with that energy value and see the solution. And what solution you will see? You will of course see the solution of basically you will plot what? You will plot solution and then colon comma 0. That means for psi. One is for psi, another is next column is for derivative of psi. That means y and z, right? So you can plot this and you can check whether this will something be reasonable for any arbitrary energy and like that. I will urge students to spend much time on this, just simple equation. I have not yet come to the trick. I'm telling that, okay, I am giving any energy you think, doesn't matter, positive, negative, whatever energy you think, you put it inside and solve the problem and check and a plot. I mean, here I'll have plot, right? Here I'll have to plt dot plot and then x versus solution colon comma 0. You just check that what it is. Okay. Obviously, you will see arbitrarily the solution is nowhere closer to the textbook solution that you should get, or you should expect. That's because energy you have not chosen properly. But how do you choose energy? Well, I'll search on a energy thing. That means my shooting will be with energy. Let me take it above because I'll write it in a definition. All the definitions I prefer to write before everything. So I will now define a function which I give it the name shoot. That means I am doing shooting practice with various energy values. I give some energy, check, give another energy, check, give another energy, check, and it should be inside. It should be inside, right? And what I should it should return. It should return me the solution of this, right? And what? And the last value, just like before, right? See what shooting mechanism, what shooting function does. It tries to solve with ODE-int. I could solve with Euler also. I could solve with Runge-Kutta also, but I did not take the trouble of writing the another few steps with all those. It doesn't matter. You know, ODE-int can solve you. And the first column, that means here it is 0th column, that is the solution. And this -1 is a last value, which I was referring at so far for the previous problem as W1, W2, and so on, right? So this is the last value. So what shoot function does, I give some energy, it shows me, it returns me where it hits on this line. where it hits on this line, where here or here or here or here or here or here, how close it is to the solution. That will show me. Okay. Okay. So this is the shooting practice. Okay. For the function is for shooting practice. Now I can tell, okay, I can now, I can take a range of energies. I can take, NP dot a range, and I can now consider from some 0 to 200. Why I'm taking this 0 to 200? It's my wish, my guess. You can start you from something to something, but I know the actual solution because I want to test the for infinite square well. I know that the energies are pi square, 2 pi, 4 pi square. So it goes something from something to, I mean, very it becomes large very soon, right? So I can test between 0 to 100, 0 to 200, whatever it doesn't matter. Okay, so this is my energy range. Energies are from 0 to 200. I will scan in this energy domain, and I call this as energies. So array for the energies. Okay, so now everything is fixed. Now, before I go here, I just test. I now test. So I now shoot with E. Okay, not only one E, I will shoot with all the energy values and check where are the last solutions. Okay, so I'll write it's called hits for all those energies. You can guess. Suppose I want to check for various energies. Now not the guess of further guess of slopes. I only here guessed one slope. See, I have not guessed here second guess. I have not gone through the interpolation, nothing, because my Eigen Energy will guide. It will automatically bring me to the solution. So suppose you are starting from here. Actual one end is here wave function, another end is here wave function. So this is the final solution, and this is the initial solution. This way, these two boundary values. So one shooting leaves you here with one Eigen Energy. Say suppose it is your with E1. Another E2 may come here. This is E2 with E2. Another E2 it may be here like this. It can be here like this. It can be here, even like this. So it can be very many different wells. Okay. So these are the endpoints here, here, all those points. For various for some value this is here, for some E1, for some E2 the value is here, and so on. But definitely for some energy the value will be very either it is directly 0 or very close to 0 for some energy. Okay, so if we now, what we'll expect if we now plot the energies, all the energies, ENERGIES, that means many energy values, all this, I mean plot with energy, and this for E1, E2, E3 and so on, and you will see for some value it's here, for some value this is the endpoints, right? This is this end value. For some value here, some value here, some value here, some value here. So for some energy it will cross the line and it will be 0 somewhere. So for example, it may like this. So here it crosses. So for that energy it is 0. I have to target that. Okay, this energy is bringing my wave function here to 0. That means it may be the Eigen Energy. And yes, we'll show you that is the case. So that means we will plot. These are the hits versus energies. Let's see that. Okay, let me run it once again. Let me run it once again. You see the numbers are changing. If you want, I can make it bigger. If you and these run these parameters, now this hits. See, it took little time. And now I will plot the hits and misses. So I will plot now the energies versus hits. I will plot now energies versus all the hits to arrays. That's it. And also I will plot the zero line to show you AXH line. This I will to show you. Let's see that. Aha, what it is. Let me put it right that way. You see that here, these are all the endpoint values. As if this is a function, you're putting the zero line at many places. So these are the eigenenergies. Here it is crossing. That means, what is this crossing means? That means here it is 0. That means 0 means what? 0 means the endpoint for that energy. Here is the energy line. This is the energy line. Some energy here. Okay. See, the energy is here, and for that the endpoint is 0. Again, some energy is here. This is the endpoint is 0, and here and here and here. So you will understand now that this is the ground state. This is the first excited state, second excited state, third excited state, and so on. If I plot it outside, percentage mat plot leaf. Suppose if we plot it outside, it will plot outside, and this is the function. You will see if you see this point, you see you just blow up this. You see this is less than 10, right? So it is pi square. Pi square is 0.87. See, this is. And the second here, suppose blow up this. This is close to where it should be 39. This is below 40, right? Here it is 40. So it's somewhere below 40. That means the first excited state. That means 4 pi square. That means 39.48 whatever. Okay. So now you believe that these crossings are actually for the eigen states. And now you know. I mean, you can from the graph itself. You can identify where is this first excited state, ground level, first excited state, second and third, and so on. If you increase the range of energies, you will find many more eigen energies. All the eigen states you can see, eigen energies you can find out from here. But if you now pick up this particular eigen energy, exact value, and put it back to the equation OD int, now you have the exact fantastic solution that you usually get, right? That's the thing. Arbitrary energy will not give you the exact the solution, desired solution. So what you do is that basically we are going to actually find out the eigen energies. This function, I will use this function, and we'll by bisection method. We don't have to do it by hand. Okay, for a complicated case, you have to then blow up the graph and can find out painfully where is the exact value. You don't need. You have the mechanism. So what you do is that basically now you need the bisection formula. Have the bisection formula, and you shoot is the function that we plot, and shoot. And we want to see from 0 to say 25. What is the eigen energy? Let's see that. And we call it En. We call it capital E, so we call it capital En. So let's see the what. Done. So let's see what is En. You see, it is 9.869. That means 9.87 something. That means pi square. If you see, well, I want to see, say, 15 to say 55, say for example, whether there is any energy. I can grossly see it from graph. You see, this is the first excited state. That means 4 pi square, 39.478 something. So now nothing. You just take this. What is the next step? You again call OD int. Again write if you x. Remember, inside U, I have two things. One is the given initial value, and one is some guess value. But the program and the numerics and whatever it is, it will not care much about this. You can actually see to it by yourself that you can give very many different kinds of values, plus, minus, as long as it is not very high or very, very low, something close to 0. So it is, it will not care about this guess value, but you have to give some guess value, otherwise you cannot start. So ux, and now you write ox equal to, now you give en. Remember, earlier we gave only e, because e was arbitrary, it's inside a function. Now I give the Eigen Energy. Of course, you have to put it a comma, because it takes in the form of a tuple. So ODE is done, and I call it solution. You can call it anything. And and now you can call, okay, your psi is basically solution, the entire solution, colon, comma, 0. That's it. And the solution is ready. And why I imported the function sims, because this function is not normalized. Of course, in quantum mechanics, you will understand from the meaning of psi, that means the psi mod square gives you the probability density, and so basically you need to normalize function in the domain always, just to have a meaningful thing. That's because you want to know that particle is here. Okay, it's probably is here. Probability is 1. So now the normalization, np dot square root, and if we call sims, psi, start psi. See, in the entire program, we have not written are using the Python machineries, Python functions and technologies, and the manipulating of the arrays. That's it. You don't feel like that you are writing a program. Keep your mind open. You have to think always that one by one, what is you are doing and how you are going to use that, and what is meaning of that. So, say normalization factor n is, say, this. So you can call it psi normal, say. That means psi by n. Okay, so this is your normalized wave function. And now the time for plot. PLP dot plot, then x, then psi, then normal. Well, this, and that's it. Simply, you just see what it is. Oh, I'm sorry. It will have to give x. What is this? Right. Oh, shine. Oh, I have not actually run it. You have to run it. Yeah. So the first excited state. If you because it was the first excited state, and the second excited state is if you give something give it somewhere, say below 100, say 50 to 100. You search another one. Say suppose you search another one. You can, but it is 88.82 something. So below 100. So you just check this. You check with how it comes. So it's a second excited state. Yeah. Okay, you'll see two nodes here, because if you draw a line, XH line, perhaps you should draw a PLP.AXH line, automatically 0. And here you see the LW equal to 3 and the color equal to, say, red, whatever. Yeah, you see, and also you could plot from 0 to 0. Okay, the box is from here to here. So it's a second excited state. So basically these are all sine functions. So these are this is the way what you do. I want to solve I wanted to solve another problem, because that is more interesting. Just in this context, I just tell you what you do. It's a quantum harmonic oscillator. quantum harmonic oscillator, right? Please tell me whenever you are through or whenever I should stop. Okay. So potential is, of course, half m omega square x square. I told you that whenever you write the Schrodinger equation or whatever, and particularly for a physics problem, you should actually rescale the problem in such a way that it is good, it is useful for you to handle. You know where is what. The differential equation is d2 psi dx square equal to 2m by h bar square, and in place of v you write half m minus e psi. It is a little different. You have m, you have half here, you have h cross, and so on. You have omega also. All these three parameters and constants are there. Okay, and energy is, you know, the exact values are n plus half h cross omega in terms of that. But this equation is rescaled, or it's called scaling, in such a way that you write m omega by h cross equal to 1. That makes us things easy. And so if you think it will be 2 it cancels. That's why we call m omega by h cross equal to 1, and the rest will go here. And so if you do that, then you can see it as that differential equation becomes, you can do it in very many different ways, but you keep track of what you are doing actually. The first thing is everything goes inside. So it is actually some x prime. I won't write x prime. I write x square only. Okay, and minus, you call it something which you call it, say, 2 into. Basically, and the energy scale becomes. See, and the energy scale becomes E by H cross. If you write E by H cross, I think the H cross E by cross. If you write E by H cross, I think the H cross E by H cross. If you take omega, m omega square common, right? All these things, so it will come here. Okay. So, and the 2 factor comes here, right? 2 factor comes here, and in the down it will be coming H cross omega, right? So E by H cross, you can think is a very nice energy scale. I mean, this is very nice to represent energy, because H cross omega, we know it. This is the this unit is energy, right? Photon energy. So you have E by H cross omega. You can call it some other, say, epsilon. So it's a dimensionless energy. So it's a dimensionless. But computer will be happy because you don't have so much things. You have all dimensionless quantities. Doesn't matter. In computer you can do anything. Dimensionless energy. Okay. So now you have simply 2 epsilon. Okay, and psi. And now your energies are, you can write it as En, and of course you understand H cross omega is 1. So En is actually n plus half. And you know now easy for you, now it is easy to locate where the energy values are, because n goes from 0, 1, 2, 3, and so on. Okay. So these are the things. So now the energies are half and so on, etc., etc. I'll tell you, the students, I'm not going to solve this problem again, because it's the same problem. You just put it. That means you have some. You have to have something. D2 y d. Suppose I write y. For brevity I write y is psi, and d psi dx, and that is, say, some z. So that means d2 dx square equal to x square minus twice epsilon y, and that means what? That means if you want to solve it just like before, dy dx, and so that is equal to z, and that is your first function, and dz dx is actually basically nothing but x square minus 2 epsilon. Earlier it was v was 0, here it is x square. That's it, and it is y, and that is your f2. Now you solve these two things in place of you go back here, you go back here. You just have to keep these things same. Only here x square minus 2e. Epsilon means just give some e, and the rest of the things are all same. But you scan the domain, you check that the energies are not very far away. That like the infinite potential well. Here the energies are half, and then 3/2, and then 5/2 in terms of odd, half integer. So you know the energy scale. You can see the energy values between 0 to 10 and things like that, and you will get back everything. Just the rest of the same, just the same. Okay. Well, should I now show hydrogen atom problem? Please tell me how many minutes I have. I cannot see. I cannot show my face, and I cannot see anyone also.
Sir, you can continue, sir. Please.
I can continue. Okay. Okay. So let's look at the hydrogen atom problem. Hydrogen atom problem. So each quantum mechanical, all are basically what we are doing very, very preliminary things so far. Step by step we'll learn. We are solving 1D problems. We are solving only not even partial differential. We are solving ordinary differential. Only thing is that our Eigen Energy will guide us, and that's why it is shooting. And because it is boundary value problem, and that's why it is a shooting problem. We actually applied shooting method, but remember, for the non-quantum mechanical problem, we had no guidance. We had no Eigen Energy kind of thing. So our guiding star was not there. We created our own guideline. So that guideline was a interpolation formula. You could solve it in very many different ways. But the idea is that you have to give it a trial and error, and shoot and have to find. In fact, this is the philosophy of life. Since our childhood, the students, we always try and fail, and that's what we gain our common knowledge, common basic knowledge. What makes what? It is not expected that we will always be perfect. We can make mistakes, and it is good that we make mistakes and we learn. So we sometimes overdo, sometimes we underdo, and finally from those, in our back of our mind, we do some interpolation kind of thing inside our mind, and we arrive at a particular solution of life or anything. Okay. In fact, this is the principle of your machine learning also. Machine also learns that way. You give it some parameter, and you try to see whether tell the machine whether this photo is of a cat or dog, image recognition. The machine will take it through the numbers. Cat means the figure means sometimes some numbers. To machine, there are some numbers. That's a numpy arrays. Some numpy arrays. Nothing more, nothing less. Some numpy arrays. 2D, 3D numpy arrays. Okay, 3-dimensional numpy arrays. One step more than matrix. So what the machine does, machine tries to understand the numbers in terms of its own weights, guess weights. So it says, it cannot tell at the first instant, cat becomes dog or elephant or something like that. It doesn't understand. It goes on doing, and repeatedly, as if it is a shooting inside. So it adjusts its parameters, and finally, one day the machine can tell, if you show the picture of a cat, it will, with some 99% accuracy probably, or depends on your algorithm, more than 90% accuracy, it will tell, yes, it is a cat. So the machine learns, machine shows the intelligence that we have, that we learned from our childhood, because we were taught by showing lots of cats and figures since our childhood. See, this is cat, CAT cat, this is cat, this is cat, this is cat. So that's why I know a cat. So this is as if shooting in our mind. Okay, anyway. So I'm sorry, I'm talking too much. Now I am going to tell you about hydrogen atom problem, but still we are only in one method only. But I'll again let me form the background. What we will solve, how much we will solve, and how we will solve. So it is a hydrogen atom problem. I'm sorry, it is a hydrogen atom problem. Okay, so if you have solved, all of us have solved hydrogen atom problem at least once in our lifetime, and we'll see the hydrogen atom problem in 3 dimensions, real hydrogen atom problem. And so r theta phi, that means spherical polar coordinate system, you more or less assume that the atom is spherical. So I will only talk about the radial part, not the other parts. Okay, so the radial part is, we'll only solve this radial part. The radial part is d2 ddr of r square dr, because the theta phi part are not interesting in this time for our thing. 2m r square by h bar square, and you have v of r, because the potential you have only r, because it's a spherically symmetric potential, and this is because it's a Coulomb potential, all directions. So, and this r is basically function of r, of course, and the right side is L into L plus 1 into r. You see the solution comes out as plus the polynomial, and so something like that, as I remember. Anyway, and yes, you solve this. We play a little trick. We put u equal to r. That means r equal to u by r, and so this equation becomes even simpler in terms of u. That's some genius people have done. So they made our life easy. H bar square by 2m minus d2u dr square, and it is v of r plus h bar square by 2m. You don't have to take the pain of solving every line, trying every line, and so on. Just accept that what I'm telling is, just believe me that it happens. You open a quantum mechanical book and you can solve it. You can arrive at such equation. And also, VR is a Coulomb potential. If you take it, say, is square by 4 pi epsilon 0. Sorry, it's epsilon 0. Epsilon 4 pi epsilon 0 into 1 by r. This is a Coulomb potential. Coulomb. And with all those, and you have minus h bar square by 2m d2u dr square. This formula, I'll tell you, this I will use it in both ways. I'll tell you. 4 pi epsilon 0. And I think I write epsilon like this, epsilon 0, and 1 by r plus h bar square by 2m L into L plus 1 by r square into, and the whole thing into u, and the right side is eu. Still, it is an eigenvalue equation. You see, right side is E. E is your energy, and it will depend on the values of lots of parameters. You see the lots of fundamental constants, H cross, H bar, M, then the electron charge E, then pi, all those are there, and then epsilon 0, and all those parameters are there. We can actually kind of reduce all those things in terms of dimensionless things, or some useful way we can reduce the equation. And also there are external parameters, L. Okay, I hope my audio is audible. I can be heard, because I am not always sure whether the internet is going or not. If
Yes, sir, you are not.
Because some phone is coming, I will always be careful. If I am not heard, then maybe one of you will call me and tell that the internet is gone. Okay, anyway, because we cannot depend on God and internet. Nothing is stable. Okay, so this is the formula. So this formula is reduced in terms of something very nice. You all know that in terms of the kind of some ways, it's called the in terms of Bohr radius. We consider the scaling in such a way. Consider the scaling in such a way. See, you could take every values and could solve. Go ahead with solving. No harm in it. But the problem is that we always have to put all those huge, these very small values and things like that. That will be a pain. In such a way that the Bohr radius A0 is taken as 1, and the energies are measured in Rydberg. I'll tell you what. Energies are then measured in Rydberg. I'll go over to electron volt also, because it's a real life problem. Okay, so what is your Bohr radius? A0 equal to, check it in any quantum mechanical book. Actually, this is epsilon 0, 4 pi epsilon 0, h bar square. And if you write m is square, so that is your 1. So that you have to rescale these things so that this ratio becomes 1. So A0 is your 1. And we choose also h bar square by 2m is also 1. And e square by 4 pi. But to make it 1, we can, because this is not in one place. Okay, somewhere it will be h bar square by 2m, somewhere it will be square by something. So the idea is, you see, if you this is the way I did. You can do it in many different ways. To make it 1, you see the components here. You see, if I write h bar square by 2m equal to 1, and e square by 4 pi epsilon 0 is such that it is 2. E square by 4 pi epsilon 0, that is 2. Okay, down. And h bar square by 2m is 1. That means h square by m is actually 2. Okay, because this factor comes many often. H bar square by 2m, right? This comes many often. Okay, so if you do that, that means your energy, it is the energy you get from exact solution, right? Energy you get is minus, I'm just showing you what it makes sense. M to the power 4 by 32 pi square, then epsilon naught square, h bar square into 1 by n square. So this is your very famous thing. So now if you now write minus m square e to the power 4 by 16 pi square epsilon naught square h bar to the power 4, this one, into h bar square by 2m into 1 by n square. You understand that. So this becomes 1. This is the Bohr radius. So this becomes minus 1 by a naught whole square into h bar square by 2m into 1 by n square. So basically, this is 1, this is 1. So basically, this is 1 by n square. So energy is a very, very simple way. You write 1 by minus n square, and you get rid of everything. This is in Rydberg. This is called Rydberg, in the unit of Rydberg. Basically dimensionless now. And if you want to convert it is in electron volt, you know the relation 1 Rydberg, the symbol is Ry, is basically 13.6 electron volt. If you would calculate all those things together, you would get that. That means energy is minus 13.6 by n square electron volt. So these are the all Eigen energies. Basically, we'll look for minus 1 by n square, and this. Okay, so the equation becomes very, very simple. d2u dr square equal to L into L plus 1 by R square minus 2 by R minus E and U. So basically, we have two terms here. Here life is a little bit difficult. Difficult in a sense, these two terms depend on the R, value of R. That means it depends on the position. And earlier you see in harmonic oscillator, it was x square. Now it is 1 by x square or 1 by R square. Okay, 1 by R. That means there is a problem. Problem is you can solve it, but you will see in lots of cases, you will yourself see there will be a lot of difficulties. It may happen. Difficulties because once you go close to R equal to 0, that means you want to go to nucleus. You want to see where, if I want to see the solution near nucleus, and this is R, right? And you see if the electron goes near nucleus, that means R tends to 0, this term will be very, very large, and the solution will be unstable. So we manage, numerically, we manage to do a lot of things, but okay. So let me check, let me first write how to solve on computer. To solve in computer, what I have to do, I have to write du dr. Again, you see it is a dy dx kind of thing, and you call it say v, and it's a function, fast function, and you call it dv dr, and that is you have L into L plus 1 by R square minus 2R minus E and U, and this is your second function. So we'll solve these two problems. But since it is a little different, let me solve this in the computer. Let's go back to our where was it? We were here. Okay, so it is a hydrogen atom problem. Okay, and this. Okay, let's again for the sake of completeness, I write import numpy as np, then from scipy dot integrate import, again the same thing. You need odint. I'm sorry, odint. You need sims. Okay. You need from scipy to optimize again. Optimize. You need to import bisect. Okay. Also, there is a function called Newton. It's a Newton reduction. You can bring both. From or import matplotlib.pyplot as PLT. So let's run it. Now, the first thing first, function where you define two functions, right? You have now U and V, so I call it, you have now U and V, two dependent variables. So I call it both of them I call it W. And in place of X, I now call it R. I now write R. Okay, doesn't matter. And you have now two parameters. See, the problem now depends on two parameters, right? This is the Eigen Energy, and L will tell you in which, whether you are say L equal to 0 is your S state, L equal to 1 is some P state, and so on. Angular momentum, right? Quantum number. So L is another parameter which will give you different Eigen energies. So I write E and L. So I write E and L. Okay, two parameters. So this is the packing of two dependent variables. This is independent variable, and these are the two parameters. The function doesn't know what is what. I give it in this order. And you write unpacking uv equal to w. You have now f1 comma f2 is actually v. So f1 is nothing but v, and f2 is all that things inside your one bar. So it's a L. Remember, it's L, huh? L and 1 looks similar, but I intentionally will not use capital L. You can use capital L. So L into L into L plus 1. Okay. Remember, this is not 1, of course. And R square minus 2 by R and minus E and star Q. These are the two functions. And of course, return F1, F2. Okay. So let's see, it is okay, flawless. Now I have to search the domain. Domain is from the art domain. Art domain, I want to check from np.lin space, and I checked with what I checked. I just do it here. You can check in your own way. In 1e minus 10, right? What is called 10 to the power minus 10, which is very, very small, close to 0, yet not 0. So we're trying to go towards the nucleus, and up to 20 I checked. You can, and 1000 points. Okay. So this is what is a scale we set. Ha. Now, remember for hydrogen atom problem, because before me, it's not my invention. I have checked through internet and many places that there are many people, many stalwarts have solved this problem numerically, numerical big bosses. And one nice trick I found, it is very nice, that often if you try to solve from this very small value towards these, the problem will be encounter lots of instabilities, lots of round of errors and so on, because all this r square down here, r is down here and so on. So what you will do is, the trick is very nice, just like Columbus's egg trick. This is, you just integrate from the opposite side. That means you take the say r prime or rr, I say. You take r colon minus 1. What does it give you? This is the array. I intentionally wrote from here to here just to tell you. I could go from here to here, but it is writing here to here is easy. And I'll also refer this the two variables, two dependent variables. And to start with, we have to give two initial values. So one we know, because one will be 0. Because so the start with, it will be 0 from the other end, because if you go far from the nucleus, that means out of the atom, it will be 0. And if you come to the nucleus, that is at the origin, it will be 0. Because now you see, the electron cannot be outside the atom, electron cannot be inside nucleus. So the two ends are 0. That means two ends serve you as two boundary conditions. That's why it is a boundary value problem. Okay. So 0, and I tried with say minus 0.001. Nothing matters. You can give anything. 0.001, 0. Usually I do not do much Kaida on this. I check, I see with try with my small value. Although the final solution should not depend on this value unless it is too big or too small. Okay. So this is a guess value. See, one guess value needed. Done. Now, actually, you can again check the energy scale. You can again find out where is the energies are crossing. Of course, analytically, you know where are the energies, 1 by n square, right? So basically, there is another trick I will tell you later, how to choose the energy scale. Because you see, the energy scale is very, it is a difficult energy scale. Energy scale, I mean, I know the problem, that's why, no? We all know the problem. The energy goes as 1 by n square minus, energy equal to actually, in Rydberg, minus 1 by n square. So the one is see 1 by 1, and the next is 1 by 2, 0.25 minus, and the 3, and then 4, 5, 6, 7, and you increase the n values, the energy levels will go as the difference will be. I mean, you know how the further and further and further they will come close and so on. This is typical different kinds of energy scale. It is not a linear scale. It is okay. This is basically a logarithmic scale. Okay, so that's why many people have cleverly suggested that when you choose the energy scale, you choose the energy scale in the logarithmic scale. In NumPy, you have linspace, you have log space. I'll show you that. But before that, I want to test for only the ground state. Okay, let's see the ground state because I will not find out the energies. Suppose I know the ground energies. So En is minus 1.0. This is the exact value. I want to see the function, wave function, okay, radial part. So the solution equal to, I mean, the searching of energy I will do it later. You can do it on your own. I can tell you the prescription that I learned. So I see I'm giving you, remember I giving RR. RR means this ulta R. RR, okay? And the aux equal to, now I have two parameters, En and L, right? So this is your solution. And so psi is solution, okay, colon, comma, 0. Is that the solution? No. The solution will be also ulta because the RR is ulta. So the solution will be colon, colon, minus 1. Okay. So again, the whole thing, the array is Eigen reverses. Okay, that's why we can now solve it. Okay, now you can find out the norm. Norm equal to, actually norm is a keyword here in Python. So I should not give this. I should give this n because in norm is a function here. Okay, we should not give some name which is so common. Sims psi star q comma r, right? So and this, and of course you have to take a square root of that, right? You have to take a square root of psi mod square. That means it's integration over psi mod square, right? And these square root, and that will give me the norm. So the psi is psi star, I mean psi by n, right? Psi by n. So that's it, done. So yeah, it is now. Let me run it. NP where? Oh, one bracket extra. I think extra. Yeah. Now now it is this. Okay. Now I can plot this. PLT dot plot R versus now psi mod square. Let me plot probability density psi mod square. This looks nice. Okay, so now it is, yeah. So this is for the ground state. If we now want to see for the first excited state, which is 1 by what? 1 by something, right? But 1 by 2 square, right? 1 by 2 square. So it is. It is. Let me say it is. Oh, yeah. It is. If you give it 1 by 2 square, 1 by 3 square, and so on, you give all these values. You, I think it is. What is it? Is let me take it as 0.25 exactly. This is the second one, right? Let me run it. Let me run it. And this. Oh, I'm sorry. Yeah. So this is the second. I mean, this is the 2s. First one was the 1s state, and this is the second s state. right? So this way you can find out all these things. Okay, so I showed in my book that there is how to find out the energy range. Here it is for the you can do it in normal ways, but the nice trick is that you actually let me tell you about R equal to, if I take np dot log space, because I know the problem here, so that's why, right? We all know log space, and suppose we want to create the values from 10 to the power minus 6 and to up to 10 square. That is very negative small value to very large value. It's lots of decades. So I can call it minus 6 because it is a log space, right? So minus 6 to 2, and I can call it say 1001. So that is your, you can choose R in that way. That means it will be easy to find out actually. Okay, and if I do that, and RR equal to R colon minus 1, okay, and then you have energies. Now you can find out energies equal to somehow I have checked that if I now give it from energy values, you search in such a way, it will be easy to find out. Otherwise, there will be long gap, you will not find out. Okay, and the minus 1 by np dot a range 1 to 20 and 0.2. Start to think of it. In fact, I gave it some more than 1, say 1.1 or 1.2 or 1.3, so that it exceeds. So that from minus 1 to something. Okay. So if it is a down is 1, so it will be minus 1. Minus 1 is our first, the ground state. So it is searching little below from that. So these are the energies. Okay. And you call it L equal to 0, whatever you do. And I will not do these things. You again write the function for shooting. Now you check this with these energies and you plot them, and you not even plot, you can actually check the values. The values will come at minus 1, close to minus 1, close to minus 25, close to minus 111, close to minus 0.625, etc. All those things will come. So this is the trick. First trick was the reverse and then do. And to find out energies, you take the R in log scale first, and the energy is 1 by this square of those things. That means it will be easy to find out because the energies are 1 by n square, right? So that's why that makes me do this, that if I search energies in this form, I will find out. Of course, you will argue that how do I know? You don't have to know. If you even do not do this, no problem. You have to take little more pain. That's it. You have to find out where those energies. You go on searching. That's it. Best thing is that I will not do these things. I can tell the students that you actually do this exercise yourself and play with this for some time to learn how we can go. I think for the shooting method, I should stop. And I do not know whether I will be given some more time. I have not touched the finite difference method. If I assume that I can quickly just tell you the finite difference method and how you can apply for your these things as a matrix or as explicit equation. I can just tell you. Okay. Okay. Should I stop or should I continue?
No, sir, you can tell.
I can tell. একদিনে অনেক বেশি ট্যাক্সেশন হয়ে যাবে আর কি।
হ্যাঁ না, আপনি এটা বলুন, কন্টিনিউ করে তারপর শেষ করুন।
Okay. Let me introduce this first. Okay. So imagine that shooting method is done, and we have learned the shooting method. But there is sometimes we cannot be we content with shooting method only. because when you solve time-dependent Schrodinger equation, then you will see that there are two kinds of derivatives. It's a partial differential equation, and you have to anyway. It's not anymore an eigenvalue equation, so shooting method will not help. So it will. You have to discretize like the diffusion equation, the Laplace's equation, Poisson equation, the wave equation. You have solved them by discretizing through finite difference method. So let me will not repeat. Let me not repeat the finite difference method, but I'll tell you the another method is finite difference method. What we do, we basically if you have u is a function of x and t, and you have del u del t, and you have del 2u del x square kinds of things. So we can actually discretize them in terms of through forward difference method, backward difference method, central difference method. And these also from central difference method. We have learned that central difference method is the best thing because the error incurred in there is the lowest. But also for a partial differential equation to solve when there are both of these things, for technical reasons, for reasons of stability and other things, we have to take some in forward difference method and some in central difference method, and all those nitty-gritty will learn when you actually deal with a partial differential equation. Okay, and just let me tell you this Newmarov method. You have heard about another method is called Newmarov method. This is nothing. Newmarov method is the it's a clever way of dealing with the Taylor series expansion and to put one into the other and finally arrive at a cumbersome, difficult formula looking, and which gives you much less error than usual this finite difference method. That's it. This is an improvement over this finite difference method. We can solve the problems by Newmarov method, but for that the derivation I have to go through the derivation to tell you. Otherwise, it will be just formula. If you look at any internet or my book or wherever, you will, or any good mathematical methods book, you will see there is a fine, nice derivations are there. You understand the derivation, you can solve the problem on computer. That's it. Okay, so let's me directly come to the quantum mechanics and finite size method. Let me talk about the quantum mechanics. In quantum mechanics, even if you have d2 psi dx square, even the potential is not there. I mean, free E psi, right? Even if you have this kind of equation, you can solve this problem by finite difference method, because you know the finite difference method. If you have this d2 psi dx square, you can write it as psi what? Psi I plus 1 minus 2 psi and plus psi I minus 1. You need 3 points, psi I, before that, after that, and this formula, and this is h square. H is your delta x. You have done that, right? And this is a central difference formula. This is the central difference formula, right? I will not go much in this. You will find out all those things. If you have still now, if I solve this, if I solve this hydrogen atom problem, if I solve this hydrogen atom problem, I will not solve this now. Problem, you will see that you had this h bar square by 2m. Basically, it is d2u dr square. So one second order term is there, and here you have minus squared by 4 pi epsilon 0 1 by r, but h bar square by 2m l into, oh, I'm writing it in a different way. Anyway, r squared u eu etc. You could rescale it etc. But you have this d2 dr squared. That means you can write it as simply you I plus 1 minus 2 ui plus ui by h square, etc., etc. And you write it for all I equal to 1, 2, 3, etc., etc. I am not going into this. You will find out this equation. You just do a little bit. You will find out these equations can be, this term can be written as a matrix form. Minus h bar square by twice m. I have not now distilled this into 1 by h square, this h square, h is delta x. And it will be minus 2, 1, 0, 0, 0, 0. And then it will be 1, minus 2. You understand the coefficients, 1, minus 2, 1. And 0, 0, 0. And it will be 0, 1, minus 2, 1, 0, 0, dot, 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 dot. You will find out this. And the last term will be 0, 0, 0, 0, 1, and 2. And this is this. Okay. And because you'll see this, this form, this thing into psi 1, psi 2, it starts from psi 1 because psi 0 is out of the context because psi 0 is 0, right? Psi 0 is one end and psi, say n plus 1 is another end. We call it, we write it from psi 1 to up to psi n, say. And this comes inside, right? And the right side is whatever, something. And this again, psi 1, psi 2, up to psi n. Because psi 0, because two ends are 0. It is inside nucleus, it is outside atom. So psi 0 equal to psi n plus 1 equal to 0. So you will arrive at a matrix. It's a matrix equation. Matrix equation. Basically, you solve this matrix. Okay. Right side is basically its term containing E minus 2m by h bar square, etc. And all the other terms will be here. Okay. So basically, you see the E is Eigen Energy. That means you solve this grand matrix through the Lagrange module in your psi pi. And we find the Eigen Energies, Eigen States, and you short them in a particular from small to large or large to short to know the ground state, first state, and so on. The case is simple, but there are, when you do, there will be little tricks. When you go on, put your hand, you will understand that. Okay, but I am not going into that thing. I'm just giving you a sketch that from finite difference method, you discretize all the derivatives, and you finally arrive at some discrete equations. You can solve it directly. If you could solve it directly, you would call it an explicit function. But sometimes you do not do that. You write it as a matrix, and you then simply take the matrix as a NumPy array and solve through some module in the Lagrange module in psi pi. So that's our task. Task is here little less, but you have to be very careful when you are solving with a real life problem, because for a hydrogen atom you are not solving a matrix of say 10 by 10 or so. You will be solving some 10,000 by 10,000 matrix. So it's an enormous task actually for the computer. So anyway, so this and last part, I'll just give a sketch of time-dependent Schrodinger equation, because here things will be moving. Okay, I'll solve it. I'll not show you the solution, but everything I have written in beforehand. I knew that time will be constant. So right, if you have I h cross del psi del t, psi is your x and t function, and minus h bar square by 2m. Now you have real partial differential equation, dx square plus vx psi x. Okay, so what you now you solve, now you evaluate with time, evolve with time, right? This equation is actually I have seen many people solving it directly, because this is one problem is it's a partial differential equation, of course, and no question of eigenvalue anything. because you evolve. You start from a packet, web packet, and you evolve the web packet. That's it. And in between, there are some potential, there are some step, there is this and that. There will be scattering and all that you know. But the thing is that the equation is a complex, not only partial differential, but another problem is a complex, and it has to be now, because now the wave function will also be complex. So you can try that the wave function you can start with a numpy array, with a complex array, complex numpy array, and go on doing this. But I have seen the problem. I don't know, some people have solved it. I have seen the internet also. Some people are solving it, getting the result, but I have checked many places and I see directly solving this complex equation will not give you the correct result always. Maybe sometimes, some cases it will give you, but the thing is that what you do is that basically is the following. You just split it into part. Real and imaginary. Psi is just two real and imaginary parts. So obviously, if you put it back, you will have two equations: one in psi and one in R and one in I. Right. So it's likewise, if you have a equation, if you equate real part and imaginary part on both sides, you have del H cross del R del T equal to minus H bar square by 2m. Del 2, they will be coupled, you see. Del 2i del x square plus v of x into psi I, and then it will be h cross del I del t equal to plus h bar square by 2m del 2r del x square minus vx of r. And of course, r is a function of x and t. And now if we solve this on a grid, that means everything will be function of xi and tj. That means we will call it rij. Also, to write it in a computer, we write it's irij. So j is the time, I is the space. So that space we usually write when I solve in computer, time on the upper. That means we immediately understand that it is the time t, time j now. Okay, these two indices. So anyway, there are some tricks, and you will have two equations for I and R. Okay, I will not go into this because we have already exceeded time for long ago. Let me just show you. For you, I have just done this. Just quickly, I tell you. Don't scratch your head by seeing this, because things are nothing. You see, you can understand everything. These are NumPy, these you matplotlib, and of course I wanted to do it animation, but you don't require animation. I mean, I do it in a very cheap way. I did not use the animation from matplotlib. You take extra jhamela for that. So these things. And also, forget about this for the time being. I used some package called Numba. It makes the array manipulation faster. I learned it just now. Anyway, I also forget that. I defined here a step function, right? And as usual, m and h bar equal to 1, 1. I defined here number of special points and time points, and this space domain I declared. Then the step function here, then the this dt, the delta t, which is I can arbitrarily choose. Many people choose it, but there is some Python, not Python. There's some numerical some estimation that if you take dt in terms of this formula, h bar square m dx square, etc., and depends on the maximum value of the potential, etc., that will guide you nicely towards a fine solution. That's a good solution. Okay, and there will be two constants involving h bar, dt, dx. Remember, dx is our h and dt is something. So k, let me call it k. Anyway, don't have to give much importance that thing. And this is some Gaussian web packet. And Gaussian web packet into e to the power ik0x. If I do that, then it will be a wave, right? Combined with a plane wave. So the Gaussian wave packet will be moving now, right? So the Gaussian function is a Gaussian function only. I'll show you. Here it's the Gaussian function. These are all parameters. Forget that. This is a Gaussian function, and again, this I have split it into cosine and sine waves. So e to the power, basically e to the power ik0x. So it's a real part is cosine and the imaginary part is sine. And I always say I just told you that instead of psi, I am solving two equations. One is for r, one is for I. It's not necessary to understand everything now. Just get the philosophy from here. And when I solve, I prefer the less number of lines and less trouble. So the program looks minimum. So I do not solve for all time. I always solve for 3 times. Present and past. I use 0 and 1 code index is for past and present, 0, 1, and 2 is for future. And then again, I renew. So every time you see if you see the equations involving R and I, you will see the time index will related to the past, present, and it gives you the future. That's it. In real life also. So so these are present, I present, R past, I past. So that's it. And the all other, these are the normalization, etc. Then plotting stuff. And here is the actual computation. And this NUMBA I have used in this way. This is a new technique. I use actually NUMBA compiler so that it makes faster, but still now it is not faster. Anyway, so let me, and here are the 2 equations. It is written not in a for loop. This is for, not even you can see time loop. Times are in 2 and 1, these indices. And these things are, you can understand, peacefully later you understand, these are all slicing. That means you need not run a for loop. So one for loop you can replace with a slicing technology. Remember those things I sometimes told you people, some of you know, or from the book, that in partial differential equation solutions, we actually made the programs look very compact with this slicing technology. Okay, so these 2 I's and R's, they are coupled, but this is the actual program. This is the actual algorithm, and the rest are all preparations. Okay, and these are updating. First goes this, R0 goes this, R2 goes 1, etc., and so on, etc. And here the time loop. This is for one time, and I make it as a definition function. Here is the time loop. Time range t plus 1. That means it goes from 0 to t. And I compute, this is the function, this is compute. Inside this compute, there is these 2 things. Done. Let's now do it. Let's now just show it. How it, if you have a little more patience of 1 minute more. So first, run, then okay, let me call run NUMBA. You don't need to know NUMBA. This, taking, okay, packet energy. It's also showing the calculation of the energy packet, and the Gaussian, you take Gaussian, and then the Gaussian into e to the power ik0x, that means the components. Also it is taking, and now you take this, and now you take normalize. Now all the plotting function also you have to call again and again. So it is also, I have made it inside a function. You can do it always. Function, okay. And now actually the definition for the computation, I also run this. And here is actually running under a T loop, under a T for loop. And here's the animation part. What I do basically is a cheap animation. I plt.cla, I clear the frame, then I plotting function, call the plotting function. Inside that, all the plotting stuff is there. I'm only plotting the probability density, and then I pause for some time and again go for another time. So every time it is creating and plotting, creating and plotting, creating and plotting. That's it. So done. So done. Now this is the last click. So now it is actually doing what it is doing. See, here is the Gaussian package. You see, it's vibrating because you cannot understand, comprehend from here that it's actually removing plotting, all these things. It's doing very fast. What it will see is that here's a step function I have created. And of course, I have rescaled the length, heights, and things to fit. And the Gaussian packet is actually approaching towards, because it's even time evaluation. It's approaching towards from left to right. Okay, and it will make a collision over here, and then you'll see how it is distorted, and then there will be some part tunneling over here, and some part remains, reflection, some tunneling. But you have to give time because I could not make it faster. I was trying last night because in my book I could not show animation, but I was trying to show you this animation. If you hold on for some time, you'll see it will be crossing. But I can end my lecture here, and meanwhile let it go, let it run, and you people can, the organizers, professors here from Fakir Chand College can go to conclude. At the end, we can see how far it has gone. Or meanwhile, you can see. If I keep my screen on, is it okay? My lecture is over. Okay.
Okay, sir.
Thank you. Let the screen on for some time. Okay. I want to show this to make people believe. You can proceed to end the session and so on. Okay. I'm done.
Sir.
I'm done.
Thank you, sir. Thank you, Dr. Avijit Kar Gupta, for this wonderful, informative talk. And I have already attended your class, actually.
Oh.
I always, I feel that you are very enthusiastic while teaching.
Yeah. Thank you.
And I wish that we could run a live question answer session, but the thing is that we are beyond time. But if audience has some question, they can ask a few questions, few minutes.
Sure,
I can give few minutes. So if you have any question, you can ask our speaker.
Yes, you've seen that it has already crossed this 400 marks and it is approaching towards this wall. And the dramatic thing will happen here when it will collide with the wall. Anyway, yeah, please go on asking questions. No problem. We can continue both ways. Sometimes we will see this, and sometimes we'll talk each other. Oh, ODINT, Moni Karna Shaha. ODINT is the famous function in SciPy, which actually solves the ordinary differential equations. If you go to because I think our regular students of whoever crossed fourth sem or so in Calcutta University, they will all know because they have used it. If you go here, as for example, if you go here on the interpreter, import from SciPy dot integrate, I was actually calling that import what is it called? ODE. So this is the integrate is a module in SciPy package, which is a very, very important, powerful package. All the calculus stuff is here. Your integration functions, your differential equation solvers. Unfortunately, it has no partial differential equation solver because partial differential equation is something very different than because you have to take care of all kinds of initial condition, boundary conditions, all mixings, all the stability conditions. So those are very, very involved. If you go to research, and sometimes your whole life can be spent on solving partial differential equations numerically, and you will see you will be an expert what value gives you what and where instability comes and so on. See, I'm actually importing this ODN from scipy.integrate. It is taking little time, and you will yourself see. If you have not used that, you will use for the first time. It is taking little time to bring. You will see that. Yeah. Meanwhile, you see. You see the dramatic things are happening here. You see, this is making a collision, and see the distributions are the fragmented, and after some time some part will enter and some part remains and so on. So this is what you find out in your book, okay? But probably animation we have not seen in our childhood, because in our childhood there was not much computer and internet and YouTube videos, but you see lots of YouTube videos doing that. Yeah, I remember Ananda Dasgupta gave one talk for some occasion. He was also solving this problem, but he did the problem with matrix method. I solved the problem with simply solving two parts, I and R, but in a tricky way. You can solve it in very many different ways. Anyway, see, from scipy.integrate, you have imported ODN. Now you see what is ODN? Help ODN. So you yourself can see, it will show you the help function. It will see function ODN. And what is that? You give function, you give the initial value of the dependent variable, you give the independent variable as t, and so on. It will show you integrate a system of ordinary differential equations. Okay, so that's what your ODN is. Yeah, please. Next question, if anyone can ask.
Sir, there is a question. Sir, can we plot more than one energy eigenvalue stepwise, like E0, E1?
Yes.
He asked this question.
Yeah, sure. We can do anything. I have not shown that, not concentrated on that fancy presentation, because it's not necessary at the moment. I mean, if you know how to plot with matplotlib, there are subplots, there are mechanisms of subplots. You can plot many functions, many eigenfunctions for different excited states. In fact, in my book, I have given some examples. You can do it yourself, and so that's very easy to do. Okay, you can do it through multiple plots. You can do it through subplots. You can always, and that's a fancy thing to do. And you can actually reproduce the textbook things. What is there in your JTL and in your Griffith or some other nice books, in quantum mechanics books, the solutions, you will get exactly that thing. But the challenge is, if you cannot solve a problem analytically, now you will take this challenge and go forward and solve this. Okay.
Okay, sir.
Okay.
Sir, I think there is no more question. So we are at the end of this webinar. Now I will.
I can now stop presentation also, because you can see this is happening.
Yes.
This is entering into and etc. You can actually. You can now believe that. Okay.
Yes, we believed. We believe in you. Yes.
Okay.
Now,
okay.
thank you, sir. And now I will request our HOD of Physics Department, Fakir Chand College, Professor Manas Mondal, to give vote of thanks.
So am I audible?
Yes.
So good afternoon, everybody. We are almost at the end of a delightful session with a lot of information and numerical techniques of how we can understand quantum mechanics with the help of Python. My wholehearted thanks to Dr. Avijit Kar Gupta for delivering such a valuable lecture, which has enriched us and enhanced our knowledge about Python coding related to different kinds of quantum mechanical problems. My sincere thanks to Dr. Somen Chanda, respected principal sir of our college, and Dr. Programmoy Pal, coordinator of internal quality assurance cell of our college, for their inspiration and constant support for arranging the webinar. My sincere thanks also to Dr. Liton Balo, Department of Electronics of our college, for technical support, which played a major role for this webinar. I am also thankful to our respected colleagues for extending their helping hands and constant encouragement in this regard. And lastly, I am thankful to all the participants of this webinar who have made it a grand success. So thank you all once again, and here I end the program. Thank you.